Typically we call this UV-Vis, and we leave off the NIR. It's mostly because we're lazy. We don't want to like say all of it. The full name of this technique is UV-Vis-NIR. And the three sections to the name are UV for ultraviolet, Vis is for visible, and NIR is for near infrared. So UV for ultraviolet, Vis for visible, and NIR for near infrared. And we call this spectroscopy. Sometimes we will call it spectrophotometry. Spectroscopy, do you know the root spectro at all? What do you recognize it from? What other words have used spectro? Or if you know just the meaning of it, that's fine too. Yes, that is a form of spectroscopy. So spectra is radiant energy. Basically meaning light. So we're talking about light. Anything that says spectro, so that's spectro over here for spectrophotometry as well. We're looking at light. Scopy is look at. So we're looking at light. That's spectroscopy. Spectrophotometry, photo is another word for light specifically. And metry is to measure. So they mean the same thing in the way that we use them typically. Spectroscopy, though, is more going to be the study of how this energy interacts, how light interacts with something. Spectrophotometry is going to be us specifically measuring and calculating how the light works instead of just studying it. It's a really, really minor kind of linguistic difference. Like, it really doesn't make that big a difference. But in UV-Vis, we are studying ultraviolet, visible, and near infrared light. In those applications. All right, so let's talk about the light spectrum here. Do you know the wavelengths of visible light?
It's from
400 to 700 or 800, depending on like who you ask. 400 to 700, do you know the unit on that? Nanometers. So when we're measuring 400 to 700 nanometers, we are saying that light travels in a wave, and the distance from one peak to one peak is 400. Or maybe it's 401 or 402 or 403. But we're saying that our eyeballs can pick up waves as long as the wiggle of that wave is somewhere between 400 and 700 nanometers in size. We can't pick up anything bigger than that. We cannot pick up anything smaller than that. Our eye detectors are tuned 400 to 700. Other things on here, visible and ultraviolet and near infrared light. Do you know where those land on the spectrum? Ultraviolet is a smaller wavelength, so it is going to be down here. The reason that it's the smaller end, even though it seems like ultra would be larger, is because in that case we are talking about frequency, not wavelength. Or not. Yes. In frequency, we are measuring how fast the light is moving with respect to its wiggles, right? So let's say I have something like that. So this larger one, and they're moving at the same speed, they're moving the speed of light, which is just one speed, right? This one is going to go peak to peak in a longer period of time than this one. So this one has a smaller wavelength and a higher frequency. Is frequency just F? I think it is. Yeah. This one has a larger wavelength and a lower frequency because they're both traveling the same speed. So UV is ultraviolet. It's ultra, like bigger than violet, because we're talking frequency. So on this scale, and I'll do this in a different color, I am choosing, this is large wavelength, and this direction is large frequency. So they're backwards of each other. And you can do in terms of wavelength, or you can do in terms of frequency. While I'm talking about it here, I'm gonna keep talking in terms of wavelength, because a UV-Vis spectrophotometer is going to measure wavelength, not frequency. So that's the unit that the instrument's gonna use, so that's the instrument, or that's the unit I'm gonna use here. UV goes from about 100 nanometers up to 400. UV is split into 3 regions. Have you heard that before? Do you know what they are? Okay. If you are purchasing sunscreen, you will see on the sunscreen that it protects against UVA and UVB. This is what the sun puts out, A and B. Well, the sun puts out a whole lot more than that, but that's what makes it through our atmosphere, is UVA and UVB. There's a third type of UV called C. Pretty easy. The breakup for those is 400 to 315 nanometers is UVA, 315 to 280 is UVB, and then 280 down to 100 is UVC. This is all continuing to be in nanometers. Do you know what is smaller wavelength than UV?
Is that NIR?
Nope. NIR is on the other side. Infrared is on the other side of the visible spectrum. It's on the red side instead of on the violet side. Smaller than that would be X-rays, and then gamma rays. For X-rays and gamma rays, instead of measuring in nanometers, we tend to measure in angstroms. And 1 angstrom equals 10 nanometers. It's a 1 unit, or a 1 decimal point change. So when we're talking about X-rays, we tend to measure in angstroms, and gamma rays are even smaller than X-rays. One way that I have found that people find it easy to kind of remember what's going on here is visible light, we know, isn't scary. It's not damaging, it's not gonna hurt us. UV light, we as people are like a little bit afraid of. It can cause skin cancer, but we can protect ourselves against it pretty easily. Like literally, like lotion is like, you're safe from UV. So we're like a little bit scary at UV here. We're pretty darn scared of X-rays. We know that those can damage our body, especially our soft tissues. And we are terrified of gamma rays. So we have this kind of like more dangerous as we get smaller and smaller in wavelength, right? The reason for that is because the smaller the wavelength, the more likely it is to mess with different parts of your body. UV messes with your cells. How do I do this? I'll zoom in a little bit and scoot that up. UV messes with your cells and makes your skin cells so they don't reproduce as nicely. And that's where we get like skin cancers. X-rays are of the size that they are going to mess with your atoms. So they're going to tear cells apart atom by atom, which is like a little bit scarier than your cells, because your cells can reproduce, but atoms, they don't just like reproduce. That's a physical property of them. And then gamma rays are going to be parts of atoms. So even more like we are destroying how things live together. And that's because like UV is large enough / small enough that it interacts with our cells. X-rays are getting smaller to the point where it's interacting with our atoms, and gamma rays are so small that it's actually passing through atoms to destroy the pieces of our atoms. So that's why we're scared of smaller and smaller wavelengths, because they're interacting with smaller and smaller parts of our bodies. So some people find that an easier way to remember like information about this stuff smaller than visible light. Above visible light. What is above red? With red is like 700-ish. What's above red? So this one. Infrared. Yes. Up here we also have microwaves. We have Wi-Fi. We have 5G, which the whole world is scared about. You'll see it's very far away from the scary side of the spectrum. Not to say that it doesn't interact with our body at all. Oh, radio waves is also way up here. So not to say that radio waves, microwaves, 5G, not to say that those don't interact with our body at all. More just to say that it is not destructive on an elemental level of our bodies. To the best that our science can tell, like the stuff that's that big doesn't interact with our bodies significantly. Microwaves interact with molecules, which is why we can use them to heat our food. Because they get the water molecules wiggling a little faster. That heats up the whole, your takeout. Infrared, just like UV, is split into 3 sections. Close to red, we have near infrared, and we're going to talk about that today. In the middle, we have mid-infrared, which that is going to be an FTIR. That's another characterization technique. And then there is far FTIR. Far IR, not far FTIR. Ignore that. We haven't really decided like very specific values where near transfers to mid and mid turns into far. At this point, we're talking very large waves relative to like where we're talking about like 280 nanometers. That's a very specific value. In IR, we're talking big enough that we don't really like notice a ton. But near generally goes up to about 2,500 nanometers. And mid goes to 25,000 nanometers. So like huge jump there. And then far is somewhere in the millions, 10 to the 6th. If we're talking millions of nanometers, at that point we start measuring in microns or micrometers, or even millimeters or meters for some of these. So we do adjust our unit as we get bigger. For the sake of today, a UV-Vis typically is going to go from like mid-range through the C up through near IR. I will just like fill that in there. So this right here is a UV-Vis-NIR, an instrument. It's going to kind of cover that range of wavelengths. That yellow is really aggressive. And then, like I mentioned, FTIR is sort of it's not complementary, but a lot of people will talk about it within the same technologies and the same projects. You'll have UV-Vis and FTIR both getting run. And that is just mid-IR, so that's just above the UV-Vis range. Okay, any questions about the light spectrum here? Okay, cool. Moving on, let's look at the kinds of interactions that light can have. So let's say I have a thing right here. It is a sample, it's a material, it's a leaf out on a tree, whatever. And I have got my light source over here. I'm gonna draw it as a sunshine. It's not always the sunshine. In fact, in UV-Vis, it's never the sunshine. It's going to be like a lamp or something emitting light. But I've got light traveling toward the thing. I'm not going to draw wiggles every single time. From this point forward, I'm probably just gonna draw arrows because that's so much less work. Okay, what are ways in which the light can interact with thing?
Can I cross? Go ahead of it, or just
Yeah.
the thing can stop it?
Yes, so that was 2. It can go through the thing, or it can get stuck in the thing. Let's talk about going through first. Going through is called transmission. And that is the light passing through the material. We can have something called specular transmission, which means that the light goes straight through, just like how I've drawn it. We can also have diffuse transmission. So specular transmission and diffuse transmission. Specular is straight through. Diffuse means that it scatters. It comes out at an angle. An example of specular transmission would be like a glass window. An example of diffuse transmission would be something like, there's a thing on the screen, there we go. Would be something like wax paper or frosted glass. It could also be something like the leaf of a plant, where you can see the sun coming through it, but you couldn't make out someone else's face through it, right? So you're getting some transmitted light through that leaf. or through a piece of paper, but it's not clear enough that you're going to be able to like tell details. And a lot of materials have a kind of a combination between some diffuse and some specular transmission.
So
Questions?
glass depends of like when does it specular transmission for glass and when it diffuse for glass?
So specifically, I'm writing frosted glass for diffuse transmission. Frosted glass would be like what you'd see in a bathroom, where it's got the like bumpy pattern to it, where like no one's gonna be able to see detail through that window because it's scattering or diffusing that light. Where a window, that like I can make out trees and mountains and such through it. Okay, let's talk about this other one that you said is it stops inside the material. That is called absorption. And there's really only one type of absorption. There isn't specular or diffuse. It's just that the light goes in and it stops. This would typically be opaque things. That is literally anything. The bark of a tree, a wall, whatever. Like, for the most part, there's some absorption happening there where the light doesn't make it all the way through. And the last type is reflection. Actually, and just like transmission, we can have diffuse reflection and we can have specular reflection. Diffuse reflection, and actually I'm going to move my sunshine over because I have not left myself any beautiful room here. Diffuse reflection is going to be something like a white wall or a desk or a wall or anything that we can see with our eyes, but we can't see details in. So everything that like our eyes see, we see them because of a reflection of light. So everything is reflecting a little bit, unless it's like that perfect black pigment. I don't know if you've ever seen that. There's like, they've made these black pigments that don't reflect any light. Other than that, which you're not going to interact with all that often, everything is reflecting at least a little. Most things are going to do a diffuse reflection. So like just light is coming back to us. We can't see a lot of detail of where the light came from. I can't see my light bulb in the white wall, reflected in the white wall. Specular reflection is going to be a mirror, where I can see the light source and all of its detail reflected directly to my eyes. Does that make sense? Okay. That also could be like glass at the right angle. We can get a direct sort of a specular reflection. Any questions about like these details here? Cool. There are ways to convert back and forth. What we could say is 100% of the light, so all of the light that goes in, is either transmitted, reflected, or absorbed. So we end up with this equation. 100% equals the transmitted light plus the reflected light plus the absorbed light. If I have a perfect system where I know none of the light is being lost, wandering off, This is a great way to convert between how much was transmitted and reflected to measure how much was absorbed. There's another couple of equations that we can use as well. One of them is absorbance equals 2 minus the log of the percent transmission. And I wrote that parenthesis too large. So that is one way, assuming there is no reflection. We also can do absorbance is equal to the log of 1 over t. And you'll notice one of them is t, one of them is percent t. So these are both ways that we can, assuming there's no reflectance at all, we can sort of like make absorbance information about a sample. Most UV-Vises will do that calculation for you, so there's no need to like do it yourself. But I think it's always a good idea to understand what it is you're doing and why. Okay, let's talk a little bit about some nomenclature when we are talking about all of these things. So you will see 3 ways that we can write the word reflect. So you will see reflectance, you'll see reflection, and you'll see reflectivity. And you'll hear people use them pretty much interchangeably. I want to measure the reflectance of this material. What is the reflectivity of this material? Basically the same, and people are going to use them interchangeably. This is another, similar to what we were talking about earlier with spectroscopy or spectrophotometry, that technically there's a difference, and if you're writing a paper, you should care about the difference. But in our spoken language, we don't care as much about the difference. So reflectance is a sample property. Which means that the value depends on, like, the thickness. Super duper thick glass absorbs a lot more than super thin glass. Reflectance, that would be absorbance in that example. It also is going to depend on like surface finish and shape. So all of those kind of things are going to affect the final result. So I would point at one leaf and I'd be like, the reflectance of that leaf is value. Then I'd point at another leaf and I'd be like, but the reflectance of this leaf is something else. These 2 leaves, even though they're the same material, have a different reflectance because maybe one's thicker than the other, or one's like dying or whatever. It's sample dependent. On the flip side, reflectivity is a material property. And that's going to have no sample dependence whatsoever. So this would be like a unit, if I was talking about the absorptivity of glass, I would say glass absorbs, I don't know, maybe like 1% per inch or something like that. Where I could be like, okay, well then my material is 4 inches thick. I know it's going to absorb 4%. That'd be absorptivity. Something that I could say glass, all glass across the whole world, as long as it has the same chemical properties, has this value. I'm not going to write it down because I don't know the actual value of glass's absorptivity and I don't want to claim that I do. But that would be the kind of example. It would also maybe be, let me think of another example. If we go back to those leaves, I could say like the reflectivity of the leaf depends on its shininess, on its smoothness. And I could create some way to factor out the smoothness of the leaf and just say leaves in general have this reflectivity. In biological applications, that's not as practical because they're really like different.
Just the ones you have.
But like the ones that you have, assume that tree is uniform. I don't know. So that's reflectivity. It's a generalized property. That one you're not going to see as often because materials do change, and the actual amount of light that something absorbs or transmits depends a lot on its geometry. So we're not going to talk about reflectivity, transmittivity, and absorptivity as much. And then lastly is reflection, absorption, and transmission. This is the noun describing the photons. So the photons that are actually interacting with the thing, going back up to the thing, these arrows that I have drawn here and here and here, those are the actual photons doing the reflecting. So this is more like a category. It's not really like a property of the material. That's why when we look in a mirror, we say, look at my reflection. What we're saying is, look at the photons of myself bouncing off of this mirror. The transmission would be, we're measuring the photons that went through the material. The absorption would be the photons that got stuck inside the material. Any questions on that? Okay. Let's see. So very generally, there's a lot of reasons why materials absorb, or like what we can learn from this. Generally, our question is, how does my sample interact with light? And that can be stuff like, I have a solar cell. And it needs to absorb light of a specific wavelength. And so I want to study what wavelength is my solar cell absorbing. We can use UV-Vis for color identification, because colors have different wavelengths that they're absorbing versus emitting. We can use it. Have you learned anything about band gaps? Yes? That is one of the genius things that make a solar cell work. A band gap is the excitation of an electron into a specific, like, highly energized state, and then it'll drop back down over time. And so we're storing energy by making that electron hop up into that higher excitation state. And because band gaps tend to happen in the UV region, we can use a UV-Vis actually to measure what energy is being absorbed by those electrons that are getting excited. So that's, like I said, usually happening in the UV. Oops. And then, like, really simply, like, we can just have material or photons get absorbed because they're lost in the material. Like, glass is so thick that it scatters the light up and down and left and right and side to side until the light just has no more energy to push all the way through the material. So there are some reasons why things get absorbed or why we maybe would want to measure. Oh, sorry, one more. Molecular bonds. This is specifically in the IR region. You are going to, some biological materials, and we've got a write-up about it on the MCL website, so mcl.mse.utah.edu. We have a blog post that talks about how IR is really useful in the food industry because foods have these molecular bonds, and you can verify whether it's like quality or purity, or even just verify like, do I have this contamination in it or whatever. And IR can typically be used for stuff like that. So molecular bonds are another reason why light interacts with samples. And I'll write down, because we talked about it. So let's talk about a little bit the inner workings. We've got like an hour, no, we've got like 40 minutes. Okay, well, yeah, plenty of time. So the inner workings of a UV-Vis. We are going to start with the source of the light. And we have two sources. I should probably put that closer to center on the screen here. I have two sources of light. One lamp, and I'm going to just draw like a little lamp shape, is called a tungsten halogen lamp. Have you heard of a tungsten halogen lamp before? Tungsten is the filament type. So we have this like really simple tungsten filament, and we're going to run some current and voltage through that filament. And that's going to cause the filament to light up, and it's going to glow. And that's how we get the most simple of light bulbs. That's how they come. The problem is this is going to spit out a whole bunch of tungsten while it works. This is why light bulbs burn out eventually, is we get these tungsten atoms flying off, and they deposit themselves on the inside of the lamp. So we end up with this like layer of tungsten. Halogens are things on the periodic table that are like chlorine, bromine, that whole column of things. And what someone really smart figured out is that if you stick a little bit of chlorine gas or bromine gas inside this lamp, it picks up the tungsten from the wall and actually sticks it back onto your filament. Yeah. So chlorine and bromine will both grab the tungsten that has been deposited on the inside of the lamp, and it'll stick it back on the tungsten using a little bit of the heat that the tungsten is creating itself. So it basically welds the tungsten back onto itself with the heat already present in the system. This lengthens the lifespan. That's why we do it that way. Yeah. I'll draw a little box around that because that is its own sort of thought. These lamps typically will emit light from about 320 nanometers up to about 3,500 nanometers, which is like mid IR down to UVA regions-ish. And if we were to graph that from 0 to like 3,500 nanometers, you'd see it's really tall and then kind of peters down. It's giving out the most light, so this is like quantity of light. It's giving out a ton of light right around 1,000. And by the way, this is not at all a linear scale of anything. It's hand-drawn. You get what you get. But we put out a lot of light right around 1,000, a decent amount of light from like 500 to 2,000. But on the edges of our scale here, we don't get nearly as much. So that's something to realize, like this limitation of like 320, I would say don't go to 320, like maybe stop at 500 if you can, or 400 I guess, because that's visible. Okay, the other lamp, we'll call it UV, and I'm gonna do it in purple because that is the color of a UV lamp.
What about blue light?
Blue light is like 500 to 600-ish, so very well within the tungsten halogen lamp range. The reason we always draw UV as purple is because the closest our eyeballs can see is violet, and that is purple. But like UV light isn't purple. It's a different wavelength than purple. It's just that's the closest our eyes can come to seeing it. Yeah. So the UV lamp is called a deuterium lamp, DT. Do you know what deuterium is? It is an element, but it's an isotope of a better known element. Hydrogen is a proton surrounded by one electron. That's hydrogen. Deuterium is a proton and a neutron surrounded by one electron. So it's just a slightly heavier hydrogen. If you ever hear people talk about heavy water, it's water where some of the hydrogens have been replaced with deuteriums. There's just a bunch of extra neutrons floating around. They don't make a huge difference on on the scale that we care about in this conversation. Heavy water is its own thing, deuterium is its own thing, but generally like fairly similar in properties to hydrogen. Deuterium lamps have a range typically less, or have a wavelength that they put out smaller than 400 nanometers. And really the limitation on the deuterium lamp's wavelength is actually the glass around the bulb. Regular window pane glass absorbs a lot of UV. So like, obviously we can't get UV light out of a lamp that's surrounded by something that absorbs UV. So depending on the lamp, we'll get anywhere from like 200 to 400 nanometers as our range for a deuterium lamp. There are some lamps that would allow you to get a little bit smaller wavelengths. The way this works, similar to how I talked about like how the tungsten halogen lamp works, is again, we've got a tungsten filament. The number of times that I talk about a tungsten filament as an integral part of some characterization tool is insane. Everything is a tungsten filament all the time. So tungsten filament is surrounded by deuterium gas, which is diatomic. So we've got two deuteriums here. And that could also be written as DT2, like two hydrogens. And we stick like 300 volts through it, ish. That was not particularly clear writing. Which causes an electron arc. So an electron flies off the tungsten, not dissimilar from the tungsten flying off in the tungsten halogen lamp. And that electron whacks a nickel anode, just a block of nickel. This electron arc passing through the deuteriums, the deuterium will excite and then relax again. So the deuterium is doing a little like energetic bump up and bump down as these electrons are passing through the gas. And that is what gives off the light, is just that excitation of the deuterium getting excited and then relaxing. It gives off a wavelength of light. So it's the deuterium itself giving off a wavelength of UV light. And like I said, it does really great down below 200 up toward 400. It does not put out wavelengths much above 400. And I could draw the same like graph like I did, but it would be from like 400 and up. So if I were to, let me actually bring that down to the neutral zone down here outside of what I was talking about there, and actually make that a little bigger. Right here I have got the tungsten halogen, and my UV lamp would be something like this. Yep, because it only does those tiny little UV wavelengths. There is a little bit of overlap between them, right around like the 400 to 500 nanometer range, maybe the 300 to 500 nanometer range. So there's a little bit of overlap. It's not a ton of overlap though. And you can see the intensity of light changes a ton. Sometimes I have really intense light, like up here. Sometimes I have really low intensity, like whenever I make that switch over here. As well as up in the IR region, I have a little bit lower intensity light. So over the course of a test, we are going to see, it's not just a constant like 80 photons of every single wavelength. So the instrument has to calibrate those things out. And there is a little bit of noise when I start, like if I start in the UV and then I switch over to the tungsten halogen lamp. So I'm like going from UV all the way up to IR. There's a little bit of noise when you switch from one lamp to the other. That's just the nature of the beast. Both of these lamps have a little bit of warm-up time that they need. The hotter these lamps get, the more efficient they get and the more photons they put out. More temperature is going to give us more photons. And this is a physical warm-up. A lot of times in instruments or computers or whatever, when we say warm-up, we don't mean like getting hotter. We like mean it needs time to stabilize or whatever. In this case, I physically mean a warm-up. It is getting warmer. And while a UV or a tungsten halogen lamp is running, you can feel heat coming off of it. So that needs some time for it to stabilize. For our instruments, we usually give them at least half an hour with the lamps on to stabilize. It's better if you can give it a full hour to make sure it's really stable. I think there are probably some people who do even more than that, just to make sure that things are like really equilibrated. After a time, they both do reach that equilibrium. They also have a limited lifespan. Both of them are expending a tungsten filament. And despite the chlorine and bromine's best efforts, we're going to eventually burn out our filament. And despite the fact that we're working with losing electrons, the tungsten filament in the deuterium lamp will eventually also wear out. For the tungsten lamp that we use, it lasts for about 1,000 hours. 2,000 hours. Got my lamps mixed up. So the tungsten lamp that we use lasts for about 2,000 hours of functioning time. Our deuterium lamp lasts for about 1,000 hours. And the total lifespan of any given lamp is going to depend on the power that you're using it at, how frequently you're turning it on and off, the exact way that that lamp was manufactured. So like there's going to be plenty of differences from lamp to lamp, but that is how ours works. There is also, from manufacturer to manufacturer, a couple different ways that the UV-Vis-NIR instrument can work. And what it comes down to is how we move the light from the lamps to the sample. In our instrument and in other like good quality instruments, you're going to have both lamps and you're gonna have some little some way to swap between the lamps. So in this situation, I've got just the light coming from the deuterium, or this mirror could swap directions. And now I have just the light coming from the tungsten. So I've got some sort of shade or mirror or something that is going to choose which lamp I'm pulling light from. I don't want to turn the lamp off that I'm not using because I don't want it to get cold. So we just have a little blocker. It's I'm using this lamp or that lamp. The light from that lamp goes through something called a monochromator. Do you know what mono means? One. monochrome means color. And while not everything we're doing on a UV-Vis is color related, like UV and IR, we stopped talking about color and we're more talking about, you know, just wavelength. But what a monochromator does is it helps us select which wavelength we're gonna grab. We have our tungsten halogen lamp is putting out this whole span of wavelengths all the time. And our deuterium lamp is putting out its little span of wavelengths the whole time. And I don't want every wavelength to hit my sample. I want one wavelength at a time to hit my sample. So inside the monochromator, I've got a prism. That prism can rotate. I'm gonna do my best. Use all my colors here. Because we're on technology, and why not use every single color? My yellow is a highlighter, so that's a little weird. And then within the monochromator, I also have these big light blockers. And as the prism turns, it's going to send one specific color through those light blockers at a time. So if I were to rotate this prism upward, I would end up with the blue also moving upward, and the blue would go through and the green would get blocked up here. Or I could move this downward so that the red is coming through, you know. So that's a monochromator. Basically a prism that's going to separate the wavelengths, and then a light blocker that's going to tell us, you know, which wavelength to pull out. There's a monochromator. They're really cool. They're in a lot of different instruments. The light coming out of the monochromator is probably going to be a little crazy. I'm probably going to have a little bit of scatter. You good? I can wait for a second for note taking. It's fine. Okay. Coming out of a monochromator, we're probably going to have a little bit of scatter. So we have these slits that'll take all the chaotic light and make sure we have just like one nice clean beam coming through. Just call that a slit. And you could move these together more or more open to get like more photons coming through. And that's, oops, way too far zoomed out. I just want to make sure I don't like run off the side of the page, because I hate when it's so wide that I like have to scroll way over to the side. I don't like that. And OneNote never stops you. It's like, I don't know where the side of the page is. Just keep writing for infinity. Then, and the next section of things is going to be a lot of like black box kind of stuff, because I don't all know how every piece of it works, but I'm going to give you the name of it so that if at any point you were like, I'm a grad student and I feel like I need to know how this piece of the instrument works exactly, you can go look it up yourself. So next we're going to have something called the CBM, or Common Beam Mask.
Why is it called this?
Because that is its name.
Does it like hide something?
It doesn't. It actually is a height adjustment. So it's going to take the light that comes out of these slits and it is going to adjust and make sure that they are perfectly aligned to go through the next kind of line of things. I don't know why. That's just how it is. And because I have hit the edge of my screen, I am going to draw an imaginary loop-de-loop. Zoom out just a little bit. I'm gonna pretend like my light just magically starts headed the other direction. In real life, we could do this, like stick a couple of mirrors in there and you could get the light to actually like make those turns. But that's what we're gonna do here for just a second. Next, we are going to have something called the CBD. No, it is not marijuana related.
Or like an order.
It's going to depend on the manufacturer and the instrument, and not every instrument is going to have all of these things, and sometimes it's going to have multiple of each things in different orders. I am giving you what our instrument has in the order that our instrument has it, but that does not necessarily mean that every instrument is going to have it, but it's a good idea to know what they are and what they do. So this is also called common beam. But this is called common beam depolarizer. Common beam depolarizer. And what's going to happen to this light while it's going through all of these different things is there is a good possibility that the light is going to become polarized. Do you know what a polarized light, what that means?
I know it's polarized, but I don't know it's polarized light.
Polarized, when we're talking about light, normally we have like light is like up and down and up and down, but I'm drawing in 2 dimensions. Sometimes it's like coming in and out and in and out and in and out like that. Maybe one is like, right? So I've got these like, if you can imagine in 3 dimensions, they can rotate along this axis. Let me see if I can draw that a little better. So a light beam can be oriented in any direction along that axis. And because of prisms and mirrors and all of the stuff going on in here, there's a possibility that we're going to accidentally get rid of all of the different orientations and just end up with one polarized direction of light. For some materials, that's okay. For others, that's going to cause some weird interactions between the sample and our polarized light beam. So we have this option to depolarize the light that's come through. Yep. So basically, this is going to remove polarization. From mirrors and prisms. This is useful for materials called birefringent. And this is a material with 2 or more refractive indices. An indice or an index in this case is like direction. So what this means is this is a material with 2 or more refractive directions depending on incoming light's polarity. So this would be a material that if you have polarized light in only one direction, that it's going to scatter the light in different discrete directions depending on that polarization. Again, really broad terms. This is if your material interacts with polarized light, we have the option to make sure that it is not polarized.
How do you know?
Mostly these materials are going to be either very well studied or man-made. So in the course of your research, you would know, how does my material react with light? Is it birefringent or not? Is it going to react with the light in a weird way or not? Got bogged down in the common beam depolarizer for a second there. Any questions though? Okay. So you may have noticed common beam mask and common beam depolarizer. Those were both called common beam. What that means is it's a single beam coming from the source. With the exception of the prism, we haven't done anything to separate or split the light coming from the source. It's just passing straight through. We call this the common beam. Our next step is to split that beam. And I have this little like prism-ish shape here. It's not exactly a prism though, because some of the light can pass through and some of the light gets reflected and then bounced, so that I end up with two beams coming out of it. We would call this a beam splitter. And I'm realizing I would like that to be a black mirror there. So beam splitter turns one beam into two beams. Why? Because, like I said earlier, our lamps are going to have different strengths at different wavelengths. So as the prism turns in the monochromator, we're going to have some wavelengths where we have a ton of photons coming through and some when there's not a lot. And the easiest way to deal with that is to make sure that the detector always knows how much light there should be compared to how much light there is. So what I'm doing here is I am creating a reference beam and a sample beam. This is something that you're going to find in high quality UV-Vises, is a dual beam system that has a beam splitter. This allows us to just compare the light that hits the sample to the exact same light, but it hitting nothing. Helps us sort of calibrate to ourselves.
Okay.
Now, the rest of the time I'm gonna have two beams. I am going to have some beam attenuators. And they have this funky little wiggle symbol on them. I don't know why, it's just the rules. The attenuators adjust intensity. So you can have higher intensity. Well, you can't have higher intensity than the lamps give, but at certain points, if they're giving too high of intensity, you can lower the intensity. Just helps give us a little bit more sensitivity. We also can add polarizers. Oh, I run out of room on the edge of my screen. We're going to do the thing again where we just like casually bounce around the corner. Keeping in mind on here that this one was the sample beam and this one was the reference beam, because I've now turned the corner and I'm running out of room again. We now have the ability also to add polarizers. So we depolarized earlier, and we can repolarize now if we want to. We don't have to install these, we don't have to use them. But that allows us to repolarize the light and potentially study how polarity affects our sample. So if I didn't know if my sample was birefringent or not, this would be a great way to study that a little bit better. Then, and I am going to draw it as a big black box because we'll talk a little bit more about it in a second. Then we have the sample and detector compartments. Detectors tends to be a PMT, which is called a photo multiplier tube. So a PMT is a really common detector type. It takes some sort of light, whether that's X-rays or visible light or UV or whatever, and it just makes the signal bigger by bouncing it back and forth against a material. Big enough to the point where it hits a detector and the detector's like, hey, I got a signal, where one wavelength wouldn't have been big enough to prompt the detector to find anything. So photo multiplier tube, photo, the like visible light, multiplier makes it bigger. So PMTs are found everywhere. There's lots of information about those. Another type is INGAS. So that's IN is indium, gallium, and sulfur. We'll also just call it an INGAS detector. And these are going to be a little bit more precise and have a different wavelength range over which they're sensitive. Boopity boop, boopity boop. And there's a couple other types, and technology is always improving. There are better and better options for detectors. Do you have questions about the lamps or the setup of the instrument?
What is the most common beam used? Like when you run a test, do you use them all? Usually.
Use what all? Like
Common
all of
beam
these
difference.
attachments and things. So our instrument in the materials characterization lab right now in 2026 has like all of these. Our instrument is a little bit older, so we have some of these probably have been improved over the years. We have all of these. You have to have a monochromator. You have to have slits. And if you have a dual beam system, you have to have a beam splitter. Other than that, you don't technically have to have any of these pieces.
So like when you run a test, do you need to change them or just run it as it is?
Nope. Everything in here that has controls is a software control. So if you turn things on and off, you can turn off the common beam depolarizer. You're like, I just don't want to use that. And that's a software control in our instrument. There are absolutely faculty members in the world who have built their own UV-Vis systems, and you literally will physically put in a CBD or remove a CBD. Our system is not like that. Our system is built in and like software enabled. We our CBD doesn't work well for the IR region, so we only use it for UV, if I'm remembering correctly. We turn everything else on, and just like by standard, our instrument just like has its preferences for like how it uses the things. We just let it do what it's best at. Awesome question. Other questions? Okay. We do not have a ton of time, but I want to talk really quickly about what the sample compartment looks like, because we talked about detectors here. There are two very common, and then a whole bunch of uncommon, like sample-specific compartments. The two most common sample compartments that you'll see is one, a liquid holder. It's got a place for 2 cuvettes. You fill them up with your liquid and reference of choice, and the light passes through them.
We need a reference.
Sorry?
We need a reference.
Yes. The reference would be the cuvette might be absorbing some of our light. So we can subtract out whatever the cuvette from the reference is absorbing.
An empty cuvette?
Yeah, usually an empty, but also you could do, let's say I have like detergent in water, and I wanted to subtract out the water and measure only the detergent. I could put water in my reference and water plus detergent in the sample. So that's very sample specific how we handle that. This measures only transmission. Assumes no reflectance. The other really common kind of holder that you will see is called an integrating sphere. I am going to draw it from the top as if we were looking down. I sort of did a weird thing with this one, like we wouldn't lay the cuvettes down the way I drew it in this like liquid holder side of things. I sort of was drawing it like, you see them, they would be standing up in the liquid holder. In the integrating sphere, looking from the top down, I have my sample beam here, and I'll typically have my reference beam somewhere toward the back. And my detector is sitting down at the bottom of a sphere. So this is really hard to draw in 2 dimensions because it's very much a 3-dimensional technique. But imagine I've got a sphere. The sample is halfway up on the sphere, so halfway out of the screen of what I'm drawing here. The detector is at the bottom of the sphere. So if you were to imagine a person holding a balloon, the knot at the bottom of the balloon is the detector. And if I were to poke the middle of the balloon, where my finger is poking, that's where the sample is. That's like impossible to draw in 2 dimensions. So if I stick my sample here, then I'm measuring the light passing through my sample, and I'm getting transmission data. See, I've got my transmission there. If I put my sample on the other side, the light would pass through the balloon, passing over top of the detector, right? Because in 3 dimensions, it's not going to hit my detector, it's passing over top of my detector. And then it's going to bounce off my sample, and it's going to bounce kind of all around the sphere It's going to do this like boing, 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 and eventually it'll settle down into the detector. So that position is going to be the reflection position. There's a bunch more things you can do with an integrating sphere. You can actually have the sample sit hovering in the middle of the sphere, where you can get transmission and reflection at all the same time. But either way, what we're doing, or what we're allowing here, is for not just transmission measurements. So we actually even could measure specular versus diffuse reflection and transmission. So going all the way back to the beginning where we were talking about specular and diffuse, an integrating sphere allows us to measure specular transmission, diffuse transmission, specular reflectance, diffuse reflectance. So we can take all of those measurements discretely and get a big picture of how our sample works. These are the most common two types that you'll see, an integrating sphere and a liquid holder. There's tons of different ways to hold a sample in the light path, but those depend on the project and the sample and aren't worth our time today. I probably should have written this earlier, but obviously the liquid holder is for liquids. And for solids with no reflectance. Integrating sphere, we can do powders, films, solids. You could technically do a liquid if you had the right holder. You could technically do a gas if you had the right holder. You can do pretty much anything in an integrating sphere as long as you can contain the sample and put it in the beam path somehow. Yeah, imagine like a cube, like a clear, like a glass jar, right? If you had a colored gas inside that glass jar, you'd be able to, with your eyes, see through the glass into the color. In this case, you'd have to choose something that was going to transmit UV. It wouldn't be like a glass container, but you could measure like, I think bromine glass and iodine gas for sure is a colored gas. So you could measure the color, measure the quantity of that gas using a UV-Vis. Something you do with the results that I wanted to say really quickly is you can measure quantity of something, use something called the Beer-Lambert law. Again, plenty on the internet about that, but Beer-Lambert law, big important thing for UV-Vis.